Welcome back. In this lesson, we're going to be looking at Newton's third law of motion, which says that for every action, there is an equal and opposite reaction. So if you are on a skateboard and you're pushing on the ground with one of your feet, you're pushing back on the ground. The ground is pushing at the same force you are back on you. If you push with more force than the ground, you'll go into the ground. Okay, so for instance, a cannonball comes in for a landing. It is going to hit the ground with such force that it's actually opposing the ability for the dirt to bounce back, and you'll end up with a hole. So if Superman hits the table so hard, he will go right through the table. Okay, so because there's a limit to what the table can do based on what the table is made out of. But as long as it's something sturdy enough, for every action that you put into something, there will be an equal and opposite reaction. I hit the tennis ball with my tennis racket. The ball is hitting my racket with the same force that my racket is hitting the ball. Okay, so all of this is going to allow us to find that there are pairs of reactions. There's something doing it and something getting it done back to them. And then you're ending up with motion based on the object of which one can be accelerated faster. Okay, so if two people are on ice skates, you have a big guy and a little guy, and they bump into each other, both of them are going to move, but the smaller one's going to move faster. So this is all a lesson on third law. First thing we're going to talk about is the fact that you can't exert a force on something without some kind of interaction with those two objects. So if you hit a bug with your windshield, the windshield is exerting a force on the bug, and the force is substantial enough to squish the bug. But the bug is also exerting an equal force on the windshield. So if you do have a force, you're going to have an interaction. So if you push the basketball with your hand to accelerate it, for instance, you're also shoving your hand back with the ball. The ball is exerting a force on your hand equal to the force that you're exerting with your hand on the ball. Newton expressed it in his third law. Whenever an object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So for every reaction, there's an equal and opposite reaction. Therefore, there is always a pair of forces. There is a pair that are opposed to each other, acting on different objects. So if you are pushing on the wall and the wall is pushing on you, the getting pushed is two different things. Then those are called action-reaction forces, and they're a co-pair with the single reaction. You push on the ball pushes on you. It's one thing happening, but two things are pushing on the opposite object. Okay? And then you can't have a force without that opposing force. They always are in the same magnitude and opposite directions, and they always act on different objects. For instance, if I push on a box and you push on a box, okay, well, that's actually two different things, because you're pushing on a box, the box is pushing on you. I'm pushing on a box, the box is pushing on me. Those are the action-reaction pairs. You can't say that I'm pushing on the box and you're pushing on the box and somehow I'm pushing on you. It's what are the two reacting objects? Sometimes these pairs are not obvious. So it's kind of easy when you say I'm shoving on the basketball is exerting a force on my hand, or the oar is exerting a force on the water, and the water is pushing the oar, which propels the boat. Sometimes it's easy, sometimes it's not. In case of, say, a car driving on the road, what is causing the motion of the car? The tires are exerting a force onto the road because of the axles of the car. The road then is actually pushing the car along due to its friction force. So sometimes they're easy to see, and sometimes they're a little bit not so obvious to see. The example here is a rocket, and a rocket can be a hard one. I think that's actually, I wouldn't have put this on this slide. If you are putting a rocket and it is exerting heated gases out the tailpipe, and those gases hit against the ground, all right, well, that makes sense. The ground is then exerting an equal and opposite force up on the system and pushes the rocket forward, okay? Just like a balloon that you let go is shoving against the air, okay? So there's air in the room, there's air in the balloon shoves against the air in the room is shoving back against the air particles in the balloon, and the balloon goes forward. In the case of going out in space, how does a rocket work? If there is nothing to oppose it, that's a little hard. What will happen is the rocket pushes on the gas. So it has expelled gases, and now the rocket is shoving new gases into those gases, and then the gases that are there at the tail of the rocket is pushing the rocket forward. So you always have to try to identify the force and what are the two pairs, what are the two parts of the pairs. So the action force, reaction force. If you can get them to where you know that they one's pushing on one, the other's pushing on one, you'll always have motion. If two things are pushing equal and opposite, say on a box, the box is not going to move. There's no movement. But if I'm pushing on a box and the box is pushing on me, there either could be movement if I'm pushing harder, or not movement if that box is so heavy that I can't push it due to its higher friction force than my strength. I like this slide. I like how it teaches. I think it's a good idea. They simply took Newton's second law, which you remember is force equals mass times acceleration, and they solved for acceleration. Okay? Now the force of the cannon on the cannonball is equal to the force the cannonball exerts on the cannon. All right, this is called recoil. Imagine you shoot a rifle, you shoot a shotgun, and your gun kicks. Why does it kick? All right, so you have an exploding gas on the inside of that barrel. The gas is pushing against, or the force of the bullet is pushing against the gas and the back of the gun. It propels forward, okay? So the bullet, which weighs a little bit, has a huge force, and so it accelerates quickly. The gun has the exact same force that was put on the bullet is put on the gun, but the gun weighs a lot, and so it has a small acceleration. The gun goes backwards, the bullet goes forwards with the same force. But the bullet weighing so much less than the gun is accelerated much faster than the gun. The gun simply kicks back, but the bullet is projected out of the barrel. So here they've got the cannonball, which is the small mass, because a cannon weighs more than the cannonball. Same force, little mass, so take a number and divide it by a little number, and you get a big number. So 10 divided by 2 is 5, right? But in the bottom number, if that mass of a cannon is huge, let's say 10 divided by 100, and now you get an acceleration of 0.1. So you see, so the smaller the mass, the greater the acceleration, and this is just a good way, I think, to show that. The headache in trying to find the action-reaction pair is that sometimes they're not always obvious, okay? I mentioned that once before. So I've got an orange. I don't know why I have an orange in a car, but I've got an orange in a car. If the orange is in the car, there's nothing the orange can do to make the car go forward because the orange can't put a force on itself. Right? In order for the cart that has the orange in it to go forward or backwards, a force has to be exerted from the outside on the cart, either a pulling force like a towing force or a pushing force, either way. So that if you sit inside your car and push with all your might onto the steering wheel, the car is not going to go forward because you are part of the car. So it's not just the car or the orange, but the orange in the car is considered one system. You inside your car can't push your car. If you want to push your car, you have to get outside the car And now the car is one system, you are a second system, and you can exert a force on the car. But if you're inside the car, no matter how hard you push, you can't do it because you're part of that system. So Mr. Apple, I guess, is pulling Susie Orange in the cart because the apple is exerting a force on the ground. The ground is pushing the apple forward, and as long as he has enough strength, he can pull the cart. It's an external force that has to move a system. You can't move a system within itself. Just to confuse you more, if you consider the system of being the orange and the apple, okay, then both of those would have to be accelerated by an external force still, okay? So the orange and the apple, if they're thought of as different, then you could have motion. If you're thought of as the same, then you would have to have an external force to the whole system because you can't move a system within the system. You have to have an external force doing it. That's why that you learned an object at rest remains at rest, an object in motion stays in motion unless acted upon by an external force. It's the same idea. You're just considering a system of objects, even if they're in motion, as one thing. Okay? So for instance, I can have a pocket watch and lots of motion going on inside the pocket watch, but I could toss you my pocket watch, and now the whole pocket watch is thought of as a system, and if I want to accelerate the whole thing, I would have to put an external force on it. So going back to the idea that the apple and the orange could be thought of as separate or as one thing, okay? Let's imagine that we're playing tug of war. I pull on the rope, you pull on the rope, okay? I pull on the rope with a certain force, and the force that you are exerting on the rope would be the same. It's actually easier if I would tie the rope to a tree. If I tie the rope to a tree and pull on the rope, the tree is pulling on the rope the same strength as I am. If I pull harder, the tree pulls harder, and you're thinking, how could that happen? How's the tree pulling? It's because it's countering my pull. That tree, I would have to be ridiculously strong to pull the roots out of the ground of a tree. So whatever amount of strength that I do, the tree opposes that strength. Okay, that's an internal system, and they cancel. So there's a canceling. The apple pulling the orange, or a kid pulling a wagon, it's the system of the road is now involved. Okay, the boy's hand pulling on the cart is equal to the pull of the cart on his hand. But if you add the fact that he's also pushing with his foot on the ground and the ground is propelling him, that allows there to be movement. So there always has to be an external force. I think I beat this point to death. So final point, if you're in the system, your forces cancel. Okay? So I push on the steering wheel pushes on me, the cart does not move. But if I'm outside and I push on the ground pushes on me, and I'm attached to the car and I push the car, as long as it's in neutral, then you might have some movement. You have to have an external force. So let's summarize. Newton had 3 laws of motion. The first one is based upon inertia, the law of inertia, and many people have memorized this, I think. An object at rest tends to stay at rest. An object in motion stays in motion unless acted upon by an external force. And that motion will always be straight line motion. It goes in the same direction as the force forever in a constant speed unless acted upon by another force. The second one is the law of acceleration, and that is that the acceleration is rooted in the ratio between the force and the mass. The bigger the mass, the smaller the acceleration. The smaller the mass, the greater the acceleration. And then Newton's third law is the law of action and action, and that is for every action there's an equal and opposite reaction. Come to the idea of a vector. A vector has 2 parts. A vector has a magnitude. Okay, so like let's say I'm going 30 miles an hour. That's a magnitude. That's how much I'm going. And it also has a direction. So if you have a velocity, for instance, which is a vector quantity, you can go 30 miles an hour east. Okay, if you know that it's 30 miles an hour, and you know that I'm going in a certain direction, then you could plot my progress. You could say, where did I start, where did I stop? A scalar quantity just has magnitude. Okay, so for instance, speed is 30 miles an hour, but if you don't know where I'm going and you want to plot my progress, the best you can do is a circle. If you knew that I traveled 55 miles an hour and I went 1 hour, you know that I'm 55 miles away, but you don't know where, in what direction I am. And so the only answer you could give me would be a circle 55 miles from the center where I started. But a vector has both magnitude and direction. So since displacement is in a direction, displacement divided by time is speed or velocity. Velocity is a vector quantity. If you divide the change in velocity by the change of time, acceleration is a vector quantity. So acceleration has a direction. So if you are proceeding in the same direction that you're accelerating, then you're going to get faster. But if you're accelerating backwards, okay, let's say I'm going left, but I'm accelerating right, then I'm going to slow down. That's what happens when you throw a ball in the air. Acceleration is towards the ground, but my motion is towards the roof. So as it gets higher in the room, it slows down and then stops, then turns around and accelerates positively down. So velocity, force, of course, is a vector since it's in one direction. Acceleration, since it's based in velocity. Velocity is based in displacement. Those are just vectors, so these terms are as well. Let's imagine that two of us are pushing on the same object. Okay, I push at a certain angle with a certain amount of force. You push a box from a different angle with the same degree of force. The box may move, but may move at an angle different from both of our pushes and at a magnitude different from our pushes. So our pushes are going to either add together or subtract. If I'm pushing exactly at 180 degrees from you, then we're canceling our forces. But if it's not at this 180 degrees, then we're adding our forces. So vectors can be added. You can add, and then the resultant is that vector line based upon the sum of the two vectors. And it can get rather messy here because you've got angles involved with this too. You're essentially going to build a right triangle, and you can use Pythagoras' theorem from math class, a squared plus b squared equals c squared, to find the vector resultant. If you've ever used an Etch-a-Sketch, you can make any line, curved line, diagonal line, all kinds of different lines, simply by two little knobs. Two knobs on the bottom, one going back and forth along the x-axis, that's the horizontal component, and then your other knob making the stylus go up and down in a vertical way. Okay, so a diagonal line is actually some right and left and some up and down. In this picture, the pink arrow is your resultant. That's the velocity that you're actually throwing a rock. I'm throwing it in a certain direction. But you can break that apart into how much of that direction is going straight out and how much of that direction is going straight up. I like to do this with geometry. Just draw a picture. Okay? Not always possible if I'm actually throwing a rock. Okay? I would actually need to know angles and stuff like that and use trigonometry. But if I have a picture, I'm just simply going to say the out part from where I started to where it ended is my x component. That's my horizontal component. The height of that arrow from where it started to the height of where it ended is my y component. So that pink arrow is made up of a small blue line forward. Okay, so some of that arrow is going forward, and a larger blue line upward. Some of that line is going upward. Now, whatever I throw up is going to get canceled because the Earth is pulling, and it would eventually arc up to a 0 point. The rock stops and then starts falling back. So it'll eat up all my vertical, but whatever my horizontal was, will show up, and we can find out how far I threw the rock. So if I know how fast I threw the rock and I know the angle that I threw it at, then I can figure out how forward that rock is going to fall. I can figure out its distance before it hits the ground again. This is Nellie Newton. Okay, I like Nellie Newton. Nellie Newton is hanging, and you've got tension in these wires. So you've got a force in the string. There's a tightness of the string. That's a force of the tension in that string. And it shows two scales so they can be measured. Okay, which has the greater tension? Okay, she has a weight that's going down. Okay, but when it gets to the ring, it's now going to be split into two parts. You can still split this up just like we threw the rock and split up the rock. You can say that part of that string is going to be a force straight up, and part of that string is a force sideways. Okay, so you can make a triangle just like you made a triangle before, and from that triangle you can figure out what is her straight up force and what is her sideways force. And then you could figure out what is the spring reading. If I knew the angle, what's the spring reading on the right, what's the spring reading in the left, in order to determine what's the tension in the rope. So here's how to solve that question with just pictures. If the red down arrow is her weight, which is a force, and the red up dashed arrow is what the ring is exerting on her body, so that's the force of tension between these two ropes, then I can simply draw a square, just like I did with throwing a rock, and figure out that the one to the left is the same as the short side of that green box, and the one to the right is the same as that long side of that green box. And so most of her weight is being held by the one closest to her, and a little bit of the weight is being held by the other spring. So if you were recording these two, you'd have a high number on her left hand and a low number on her right side.